Well, let's take a look at a simple circuit that utilizes an operational amplifier. To build this circuit, we'll begin by connecting the positive terminal of the op amp to ground. So I'll show this in the diagram by connecting a wire between that terminal and ground. Next, we'll attach a resistor to the negative input, and we'll assign a resistance value R1 to that resistor. And then, to ensure that we have negative feedback in this circuit, we'll take the output and feed that back with a resistor of some resistance R2 in the feedback. And then we'll define the input voltage as the voltage relative to ground at this side of the resistor R1, and we'll define the output voltage as the voltage relative to ground at the output of the op amp. Well, this operational amplifier circuit is employing negative feedback. That is, we're taking the output and feeding it back to the negative input. When that happens, we can use the model that we've developed earlier for an ideal op amp. And the two main ideas that we use in this model for ideal op amps is first that the voltage at the two inputs, the positive and negative terminals to the op amp, are equal. The second is that the current flowing into or out of either of those terminals is zero. So in this case, we have the positive terminal connected to ground, so that's going to give that a voltage of 0 relative to ground, which means that this point is at 0 relative to ground. So the voltage here is 0 relative to ground. The next thing we know is that the current flowing through here is 0. And what this means is that any current flowing in this direction, in from our source, call that I, none will go into the op amp, all of it will flow this way. So let's see if we can figure out what I would be. Well, let's see. I is the current flowing through a resistor with resistance R1. The voltage on this side is Vin. The voltage on this side is 0. So that current, I, is the voltage that drops in the direction of the flow of the current, which is Vin minus 0. So that's Vn divided by the resistance, which is R1. Now we know this current, so we know that there will be a voltage drop from this point, from this side of the resistor to that side of the resistor, equal to this current times R2. So 0 minus V out, so that's going to be negative V out. That's how much the voltage drops from this point to this point in the direction of the flow of the current. That's going to be equal to this current times this resistance. Well, this current is Vn over R1, so we can rewrite this from these two equations. We have that V out is negative I times R2, but I is Vn times R1 over R2, so we'll write this as negative R2 over R1 times Vn. So this output voltage is the input voltage negated, inverted in polarity, times the ratio of the resistors R2 to R1. So if we want to amplify this input voltage, make it larger, we'd make R2 greater than R1. If we want to make the input voltage smaller when it comes out, then we would make R1 greater than R2. But in both cases, we'll invert the voltage. So positive voltage here would be a negative voltage here, and its amplitude would be determined by the ratio of R2 to R1. Well, now let's take a look at another op amp circuit. For this circuit, as I did with the previous circuit, I'm going to take the negative input terminal and provide feedback through a resistor to the output. So rather, the output is feeding back to the negative input terminal, and I'm going to assign a value for this resistance of R2. Then I'm going to take this negative input terminal, and I'm also going to put that through another resistor and connect that to ground. And I'll call this resistance R1. Then I will take the positive input terminal, and to that I'll connect an input voltage Vin relative to ground, and I'll define my output voltage here as V out relative to ground. And what I'd like to do, just as I did with the previous circuit, is determine how V out is related to V in. Well, because we have negative feedback, we can use the model for an ideal operational amplifier. So the current flowing in this direction, in or out, is 0, and no current flows here. Now the voltage at the positive terminal is Vin. We've connected directly to our input voltage, so that means the voltage at the negative terminal would be Vin, and that's also this point, so I'll call this point Vin. Now no current flows through this region, so any current flowing to ground, for instance, is going to flow through this resistor in this way. None of this current can flow here because no current flows into the op amp. So if I define this current as I, then that overall current, I, would be equal to V out over R1 plus R2. But that would also have to be equal to V in over R1. So if these two are equal, then V out is equal to R1 plus R2. So I'm going to set these two equations equal, divided by R1 times V in, which would be equal to 1 plus R2 over R1 times V in. So in this case, we're not inverting the input voltage, but we are amplifying it, and the amount we're amplifying it by is equal to 1 plus the ratio of R2 to R1. So if we make R2 much smaller than R1, we're just simply following the voltage out. If we make R2 significantly larger than R1, then we can add some amplification to the input voltage. Well, let's look at one more circuit. As we've done with the others, what I'd like to do is take the output and connect it to the negative terminal for the input with a resistor, and I'll assign a value of R2 to that resistance. And then I'm going to take that and put another resistance R1 here, and then I'll label this input voltage V1. Now I'm also going to take the positive terminal, and I'm going to drop down to ground with the resistor of value resistance R2. So this resistance is equal to this resistance. And then I'll go out with another resistor of resistance R1 equal to this resistance, and I'll call that input voltage V2. So now we have two voltages input to this circuit, and the output I'll call V out. Now again, because we have negative feedback, we know that these two voltages are the same. So let me label that voltage V0, and that'll also be V0 here. And we know that no current is flowing into this positive terminal, no current is flowing into this negative terminal. So any current flowing from V2 inward will go right to ground. any current flowing from V1 will move right around here and go this way. So let's see if we can write an expression for V0. Well, in this case, the voltage across R1 and R2 is V2 minus 0. And then this voltage from across R2 is just V0. So we could write an expression using voltage division that V0 is equal to V2 times the ratio of R2 over R1 plus R2. So again, this is the voltage across resistor R2 by voltage division. Now, across these two resistors, the total voltage is V1 minus V out, and the voltage across resistor R1 is V1 minus V0. So let me write this one as V1 minus V0. So that's the voltage across this R1 resistor. So the voltage from this point to this point, that's going to be R1 over R1 plus R2 times the voltage from this point to this point. So that voltage is V1 minus V out. And then the voltage division is R1 over R1 plus R2. Then what I'll do is rewrite the second equation as V0 is equal to V1 minus V1 minus V out times the ratio of R1 over R1 plus R2. So now I have an expression that says V0, this intermediate voltage, is V2 times R2 over R1 plus R2, but it's also V1 minus V out times R1 over R1 plus R2. So I'll equate those two expressions and see if I can get an expression for V out in terms of V2 and V1, the two inputs. So let's see, we have V2 times the ratio of R2 over R1 plus R2, and that's equal to, well, that's V0, so V0 is also equal to V1 minus V out times R1 over R1 plus R2. Oops. That's an R1 plus R2. Now I'm going to multiply both sides of this equation by R1 plus R2. So that'll give me V2 times R2 is equal to, well, multiply this side by R1 plus R2, we'll have a V1 times R1 plus R2, so that's V1 times R1 plus V1 times R2, and then minus, when we multiply this part of the equation by R1 plus R2, we'll lose the denominator and we'll have R1 times V1 and R1 times V out. And we've got a negative sign here, so this will be V1 times R1, and then a negative, that'll be a positive V out times R1. So now, if we take that equation and solve for V out, what we'll find is that V out is equal to, well, we'll have the ratio, just doing algebraic simplification of this, R2 over R1 times the difference, V2 minus V1. So the output voltage relative to ground is the difference of these two voltages relative to ground multiplied by the ratio of the resistance R2 to R1. So if R2 is equal to R1, the output voltage will just be the difference between these two. If R2 is twice as big as R1, we'll get twice their difference. So this is the operational amplifier circuit for a differential amplifier.